put it simply, air transportation is important. To put it precisely, air transportation is the muscle behind the striking force of our air arm. Constant improvements in engine design help the fist strike harder and harder, and constant improvements in engine design for the supporting muscle, air transportation, are no less important. The engine designer's objective is power for progress, an unending search for the best, most efficient power for flight, a continuing study of factors like speed, weight, shaft horsepower, aerodynamic drag, and operating costs. This is the engine designer's constant challenge. For instance, the reciprocating engine is today's most efficient and most complex. The turbojet engine is today's most powerful and most simple in basic power section design. Somewhere in between lies a new kind of power for flight, an engine with the inherent power section simplicity of the turbojet, but providing also the high thrust efficiency of propeller power. And here is the engine designer's solution to the problem. A new kind of power for flight, the turboprop engine. More power and speed, less weight and aerodynamic drag, lower fuel costs. Here is power for progress for many types of aircraft. For greater speed, increased payload, shorter takeoff and landing runs, high rate of climb, and most economical overall operation at all altitudes. A turboprop, like a turbojet, is a gas turbine engine. Air is compressed and delivered to the combustion section. There, fuel is added, and the mixture is burned. The expanding gases release tremendous amounts of energy. In a turbojet, a turbine absorbs only the amount of energy necessary to operate the compressor and engine accessories. The remaining energy becomes jet thrust by reaction from ejection of the exhaust gas at high temperatures and high velocity. In a turboprop, the turbine is designed to absorb maximum energy from the expanding gases. This energy is converted to shaft horsepower and used to drive a propeller through a reduction gearbox, as well as the compressor and engine accessories. About 10% of the turboprop engine's propulsive force is jet thrust, but all the rest, the main propulsive force, comes from the propeller. The turboprop engine has many advantages over the compound reciprocating engine of comparable power. First, it has less than 1/3 the cross-sectional area, and therefore less aerodynamic drag. Second, in terms of power to weight, the turboprop holds a 2.5 to 1 advantage. The compound reciprocating engine delivers about 1 horsepower per pound of weight. The current turboprop delivers 2.5 horsepower per pound of weight, and this engine has ample room for power growth. Third, the two engines are roughly comparable in the use of pounds of fuel per horsepower per hour, even today. But whereas the reciprocating engine requires high-octane gasoline, the turboprop, like the turbojet, can operate on any good turbine fuel, which not only costs less, but is in far greater supply. Moreover, the engine's lower weight permits routine check work and minor overhaul on the engine itself, and less work is required on the airframe because of reduced vibration. Fifth, the simpler design of the turboprop results in more horsepower per dollar expended in manufacture. The difference in cost is almost the equivalent of 1 spare turboprop for every 4. These then are some of the advantages of the turboprop engine. Advantages which mean progress in aircraft power for air transportation. Let's see how this new kind of power has already reached practical availability. Development began with a request from the Navy Department, Bureau of Aeronautics. But the request wasn't for a specific engine. It was for any engine that would enable an airplane to meet certain specific requirements. This took an engine with high power, low weight, small size, low fuel costs. This request was for an engine which would enable an airplane to perform missions not possible with any known engine. And detailed study ruled out either the reciprocating engine or the turbojet. And so a new concept was born, the turboprop engine. The specific Allison proposal was for the T-40, an engine with twin power sections driving a contra-rotating propeller which could be clutched to either or both power sections for unusual flexibility of operation and economical cruise. To expedite development, the T-38 was then designed, with gearbox and propeller driven by a single power section. Following tests of component parts, testing of the complete unit proceeded until the engine was ready for flight evaluation. A test bed was installed in a B-17. Standard flight evaluation tests were made, including tests for temperatures and pressures throughout the engine. One result of this work was the development of simplified coordinating and propeller controls. And the next step was to prove the turboprop engine as a practical power plant on its own. Military interest in the advantages of turboprop power for both existing and future aircraft had reached the flight test stage. For instance, the Convair XP-5Y flying boat, the Douglas XA-2D Sky Shark. Could turboprop power do a job in these planes? Well, let's see. The XP-5Y long-range flying boat, built by Consolidated Vultee Aircraft Corporation, was the first American aircraft to fly wholly on turboprop power. The 4 Allison T-40 engines and dual rotation Aero Products propellers give this 70-ton transport a power-to-weight ratio far in excess of many World War II fighters. It was test flown to evaluate the production version, the R-3Y Tradewind. The XA-2D carrier-based attack plane, built by Douglas Aircraft Company, was the first American turboprop-powered bomber to fly. The Sky Shark is powered by an Allison T-40 engine with dual rotation Aero Products propeller. The XA-2D can carry a greater payload than any known jet bomber or fighter for the same expenditure of fuel. The testing program on the XP-5Y, the XA-2D, conducted by the aircraft manufacturers, provided the first turboprop flight test effective data accumulated in America. Allison also engages in flight testing on its own, following the long-established General Motors policy of proving new products in the vehicle of proposed use. In 1950, Allison purchased a standard Convair 240 for test purposes. One T-38 model turboprop was installed in each nacelle by Convair, and this became the Allison Turboliner. Because of landing gear design and other practical considerations, the standard nacelles were used. You can easily imagine how much smaller the nacelles would be in size and cross-sectional area if designed for an optimum turboprop engine installation. Ground running began in November 1950. 3 months of vibration and stress analysis uncovered no adverse vibrational characteristics in the engine, propeller, or nacelle. Early flight tests, coordinated with the ground running program, began in December. Flight information, accumulated during hundreds of operating hours to date, has resulted in further proof of the advantages of the turboprop engine and provided valuable information leading to still further improvements in engine design. Remember that in the early phases of its development, the advantages of the turboprop engine were largely demonstrated by the T-38 and the T-40. Now let's look at the T-56, an advanced model sponsored by the United States Air Force. Progress in design has resulted in more power, higher possible flight speeds, and improvement in fuel consumption. Let's consider in some detail the specifications and characteristics of this representative turboprop engine. Weight is 1,550 pounds maximum. Total length is 145 inches. Width, 27 inches. Height, 39 inches, or 34 inches with the gearbox offset down. This choice of gearbox position, up or down, gives further flexibility to the designer in location of the power plants and centerline of propeller thrust. As a further option for the designer, accessories may be top or bottom mounted on the power section. A constant speed engine in flight, the T-56 is rated at 13,820 RPM through all operating phases. And here are its power ratings. First, takeoff power at sea level static conditions. Propeller shaft horsepower, 3,507. Jet thrust, 608 pounds, making equivalent shaft horsepower, 3,750. Specific fuel consumption is 0.546 pounds per hour per equivalent horsepower at takeoff. Second, normal cruise power at 30,000 feet and 300 knots. Propeller shaft horsepower, 1,750. Jet thrust, 125 pounds, making equivalent shaft horsepower, 1,875. Specific fuel consumption is 0.450 pounds per hour per equivalent horsepower at this operating condition. The 14-stage all-steel axial flow compressor handles more than 30 pounds of air per second at a compression ratio of more than 9:1. The combustion assembly consists of 6 inner burners within a steel outer shell. Individual fuel nozzles feed each inner burner. Once started, burning is continuous. Most of the energy from the hot gas is absorbed by the 4-stage turbine. The remaining energy results in thrust as the gas is ejected. The power section drives the integrally mounted reduction gear assembly through an extension shaft. In a 2-phase step-down, the reduction gear assembly reduces power section speed to optimum propeller shaft speed in a ratio of 12.5:1, from 13,820 RPM down to 1,106 RPM. At the point of connection between gearbox and extension shaft, a safety coupling is provided. It automatically separates gearbox and power section if ever a negative torque of predetermined magnitude should be transmitted through the propeller. The safety coupling automatically re-engages when the gearbox speed matches that of the power section. The pilot has to move nothing but the power lever to change the power setting for a particular operating condition. Power adjustments are made through the engine coordinating control, which automatically coordinates fuel flow and propeller blade angle. The engine fuel system features a dual fuel pump arrangement. If the operating pump should fail, the bypassing second pump automatically overrides to provide the necessary fuel supply. Now let's consider what all these advantages of the turboprop engine mean in terms of operational characteristics. For instance, operational simplicity. The piston engine pilot has many operating controls to keep in manual coordination for every phase of operation, from starting to landing. The turboprop pilot has but one operating control, the power lever. A mechanical electrical coordinating control mounted on the engine automatically provides for all requirements of ground and flight operation. The pilot, in turn, is automatically provided with a full range of thrust selection, from 0 to maximum positive, and from 0 to maximum negative. We shall see how useful this is in a moment. Here's another operational characteristic. In flight, the Allison turboprop is a constant speed engine, while in ground operation, engine speed is variable. And starting is simplicity itself. After the normal presettings are made, the pilot simply selects Start with the power lever, then pushes the start switch. Now a self-contained starting unit takes over. In a matter of seconds, the engine fires up and stabilizes at ground idle RPM. At this operating condition, the propeller is delivering zero thrust. The extremely useful range of thrust selections soon becomes evident. Complete control of the airplane is achieved through smooth, continuous changes in thrust values, from positive to negative. For instance, takeoff runs in the Allison turboliner have measured out to less than 2,000 feet. Rate of climb is 2,500 feet per minute at an indicated airspeed of 220 miles per hour. Instantaneous availability of full thrust is especially important in go-arounds. With the constant speed turboprop engine, full takeoff power is immediately available for emergencies. During letdown, coordinated control between the fuel regulator and propeller permits a steep angle of descent. As the power lever is retarded, the coordinated effect of reduced fuel flow with the propeller governing to maintain 100% RPM sets a high engine speed and flat blade angle, which produces the desired braking effect on the airplane. Immediately after touchdown, moving the throttle back to the start position sets the propeller to minimum torque blade angle, markedly increasing the drag effect. Now, to further shorten the landing run, the pilot selects reverse thrust. Up to 80% of takeoff power is available in the reverse regime. These are some of the primary operational characteristics of turboprop power. The T-56 turboprop engine, then, with its advanced design, power rating, and operational characteristics, is the key to the future for military and civilian air transportation. The first United States Air Force transport designed specifically for turboprop engines is the Lockheed C-130, powered with 4 Allison T-56s. Planes like this can fly faster and higher for high-speed, long-range personnel transport, as cargo planes for heavy equipment, as hospital planes for litter cases. And thanks to shorter takeoff and landing runs, they can operate in unimproved forward areas. Another application of turboprop engines in the transport field is the C-131C, a conversion of the twin-engine Convair 340 to Allison T-56s. Usefulness of turboprop transports is not limited to military application. Commercial operators also look to these new type aircraft to carry greater loads at higher speeds and with better economy. But the future of turboprop engines has only begun. The basic power section can be adapted for marine power, stationary power plants, the helicopter, and other vertical takeoff requirements. For all high-speed, load-carrying flight requirements, it seems inevitable that turboprop engines will supplant piston engines in military and civilian aircraft. The Allison turboprop engine, simple, compact, and powerful, opens new horizons of power, efficiency, and performance. It's today's power, today's new power for flight.